Okay, so we're going to talk about graphical differentiability. So in the previous video that you were watching, that talked about the fact that you could not have a derivative at a sharp turn on a curve. What's really important about this for the AP exam and for any question that you complete in this class is that you understand that a derivative, by definition, is a two-sided limit. So for this particular problem, if we're looking at the function f of x equals the absolute value of the quantity x minus 1, and we're looking for the derivative at x equals 1. We know just from the previous video that we can't have a derivative at a corner or sharp turn. However, it's very important for us to understand why. Derivatives, by definition, are limits of the secant slope. That means we're trying to take a limit as the delta x, or the x, approaches 1, or the delta x approaches 0. And the delta x is really what that h represents all the time. Now, the problem is that the right-hand side has a slope of 1, and the left-hand side has a slope of negative 1. So what that means is the limit as x approaches 1 from the left of the derivative function of x is equal to negative 1. And the limit as x approaches 1 from the right, not of f, but of the derivative function, is positive 1. So since the right-hand side derivative and the left-hand side derivative are not the same, we have to say that the derivative at x equals 1 does not exist. So if we were to graph the function, again, this function is y equals the absolute value of the quantity x minus 1. If we graph the derivative, the entire side on the right-hand side is 1, and the slope on the left-hand side is negative 1. So a graph of the derivative function would be piecewise. For x greater than 1, the slope would be 1 the entire time because we have a linear function, so it has a constant slope. The left-hand side is also a linear function, but the slope is negative 1. Because the left and the right don't match, we actually have an open circle here. So we can't try to choose between the left and the right and assign one. We actually have an open circle on both sides. At x equals 1, the derivative, which is a limit, does not exist. Now, for a different reason, we can also have functions that have no particular slope. What you have to be very cautious of with a function like the cube root of x minus 1 is that your calculator would actually make a mistake and tell you that it thinks the derivative is 100. That's not actually true. What your calculator is doing is it's finding the derivative really close by. Remember we talked in a previous video about how your calculator really doesn't know algebra, so it can't really do its best job taking a derivative. Algebraically, it can only approximate, and it's trying to approximate by using each side of the derivative. The problem is we now know the power rule to take this derivative. So I could say that my f of x was x to the 1/3 minus 1. The power rule tells me the derivative is 1/3. X subtracting 1 from the power makes it negative 2/3, and then minus 0. So my derivative, in fact, is 1 over the cube root of x squared. Now, the cube root function itself is defined for all real numbers. So the domain of this original function is all real numbers. The problem is that my derivative isn't defined for all real numbers. If the denominator is 0, then I have an undefined derivative. So f prime of 0 is a derivative, which is a limit. Remember, derivative by definition is a limit, so the limit does not exist. As a matter of fact, we notice that the original function, when we just did the cube root of a negative exists, and it's still negative. However, when we square the cube root, that makes everything positive. So notice on this graph, all of the values are above the x-axis because the derivative is always positive, except at x equals 0. And because the entire derivative is positive on both sides, we would have a derivative that's approaching positive infinity. So notice what your calculator did. It found the values as close as it could try to get to 0 and thought it would average them out and get 100. But that would actually be incorrect. So you have to be very cautious that you're not using your calculator to try to figure out if derivatives exist. In fact, this particular graph would have a vertical, extremely steep, so we have a vertical tangent line because we do end up having a point, but it's so steep that it's a vertical line. Try not to get confused, though, between having a vertical tangent and a vertical asymptote. A vertical tangent is when f of a exists but f prime of a does not exist because f prime has a vertical asymptote. It's a little tricky. So when the derivative has a vertical asymptote, the original graph has a vertical tangent. When the original graph has a vertical asymptote, there's no f of a. So if f of a were undefined, because you have a vertical asymptote, not because of a jump, then you simply wouldn't do the derivative at all. Okay, the third way that we could end up with a problem isn't because the function is continuous, it's because it's discontinuous and we failed to check. The most common mistake I see students do is they try to jump to differentiability by taking the derivative. Before you can ever do differentiability, you must first check continuity. These look good because if you look at the left-hand side and the right-hand side, you are going to get the same values. 2 minus 2 would be 0, and 2 minus 2 would be 0. So those both look great. However, we have a function that is discontinuous. So even though we have the same slope on each side, we do not have a differentiable function. We have to remember that differentiability is not guaranteed. So it's not possible without continuity. There's another slightly tricky thing about this that confuses people frequently. If f of x is differentiable at x equals a, then f of x must be continuous. At x equals a. This is not true in reverse. If f of x is continuous at x equals a, there's nothing guaranteed about differentiability. For example, our absolute value function, continuous for all real numbers, not differentiable at the vertex. So differentiability guarantees continuity, but continuity by itself does not guarantee differentiability. So if we look at this previous one, if I simply try the continuity part first, which is absolutely required as the first step, I would not have gone on to do the derivatives at all, because the limit, as x approaches 1 from the left, uses the x squared minus 2x plus 1, gives us 0. The limit, as x approaches 1 from the right, uses the function 2x minus x squared, gives us 1. That means that the two-sided limit as x approaches 1, f of x limit does not exist. Therefore, f of x is not continuous at x equals 1. Therefore, f of x cannot be differentiable at x equals 1. So, in order to determine differentiability, you must follow these steps in order. You must check to see if the function is continuous. If the function is not continuous, you stop. If the function is continuous, you go on to step 2. Does the slope or derivative exist on the left and right sides? If so, do these slopes match? And then, is the tangent line vertical? Vertical lines have undefined slopes. A function is never differentiable if any of the following occur. If the function is not continuous, there can be no tangent line at the point. If the function has a sharp point, you do have continuity, but your derivative cannot exist. There is no tangent line at that point. If the derivative of a function is undefined, because it's so steep it appears almost vertical, then you do have a tangent line, but the derivative is not defined, so the derivative does not exist. So not differentiable for any of these three reasons. So we would not be differentiable if we were not continuous. At B, we have a jump discontinuity. Therefore, we have a not differentiable. At C, we have continuity, but we have the limit does not exist. So the left C of the derivative does not equal the right slope So we do have continuous here, The function left and the function right and the function value are all three the same, but the derivative doesn't match on the left and the right. So we have continuous but not differentiable. Finally, at C, we have continuity. Left equals right equals function value. However, the derivative does not exist because we have an undefined slope. So when we have a vertical tangent, that means we have an undefined slope. So the limit, or the derivative, which is the limit by definition, does not exist. Be sure you understand the different ways you can have continuity without differentiability and how you could have no differentiability automatically because you don't have continuity. Make sure you're always testing for differentiability by first testing for continuity. Okay, so hopefully you watched the instructions on how to use your calculator. There was a great YouTube video on how to take derivatives using your calculator. Some of these I would definitely look at specifically based off the graphs. The absolute value of 1 minus x at x equals 1. The function is not differentiable. We do have continuity, but we have the sharp turn. Now on the AP exam, the way that you're going to represent that you have a sharp turn is the limit x approaches 1 from the left, not of the function, but of the derivative, does not equal the derivative on the right. But derivatives by definition are limits. So you're going to work through these with your calculator to graph the function. So you're graphing these on your calculator to determine whether or not you think you have a derivative. Another way to think about these is to rewrite them. Some of them can be rewritten. And recognize that if you take the derivative algebraically, that when we have these fractional powers, it is very frequent that we end up with a denominator of 0 that wasn't there before. So 1 through 8, you're going to work graphically. Now, we're going to look at number 9 together. So for letter A, remember we must first check continuity at all times before doing differentiability. So we're going to do the limit as x approaches 2 from the left of the original function. And then we have our left and our right. Remember, right is the one that's greater. We substitute 2 in, we get 4 plus 1 is 5. The limit as x approaches 2 from the right, the original function. We substitute 4 times 2 is 8, minus 3 is also 5. We must check the function value at 2 because sometimes you don't have an equals. So if you had an open circle, you would not have continuity. Now f of 2 uses the top function, so 2 squared is 4, plus 1 is 5. So therefore, f of x is continuous at x equals 2. That means we can move forward with differentiability. So now that we know shortcuts for derivatives, we're going to take the derivative of the function piecewise. Now, what's really important is we're determining whether we have differentiability. We do not put an equals here unless we determine that yes, the derivative exists. We don't know the answer to that yet. So I take the derivatives and I leave this as open. I have my left and my right. So the limit as x approaches 2 from the left of the derivative this time. The left-hand side is 2 times 2 is 4. The limit as x approaches 2 from the right of the derivative, so watch your notation, is the constant value of 4. Since we had continuity and the derivative matches, we can now say f prime, that looks like an inverse function, let me fix that. F prime of 2 does exist, and it equals 4. We need, for continuity, a left limit, a right limit, and a function value. For differentiability, we need continuity and then just a left limit and a right limit. Okay, so for B, first I'm going to check continuity. So I'm going to label left, right. So from the left, the original function, 2 divided by 2 is 1. 1 plus 1 is 2. X approaches 2 from the right, the original function. Notice, be very careful, this is not the square root of 4. The x is not under the radical. That means I have 2 times the square root of 2. The function value uses the lower part, which we already know is 2 root 2. So the two-sided limit of the function value does not exist because the left and the right don't match. Therefore, f of x is not continuous at x equals 2. Therefore, f of x is not differentiable at x equals 2. And we don't take a derivative at all. For number 10, where does the limit fail to exist? The limit only fails to exist if the left doesn't equal the right. So the limit fails means left does not equal right. That only happens here at 1, 2, 3, 4, 5. So x equal to 5 only. Fail to be continuous means we have left, right, and the dot. So obviously, if the limit doesn't exist at x equals 5, we definitely have a jump discontinuity there. We also have a limit existing, but then not continuous because of the dot at x equals 3. Fail to be differentiable automatically anywhere that we're discontinuous. So we had to include both of the discontinuities. Then we have to scan across. We do have a smooth turn, it appears here. So that one works, but we can't have here. So x equals 1 is also going to be added to our list because we have continuity, but the slope on the left doesn't match the slope on the right. So yes, continuous, but not differentiable. We have no continuity here because we have a hole, but we do have a limit. Here we have no limit, so automatically no continuity and no differentiability. Okay, the last question says, where on the interval is the derivative equal to 0? A lot of people would like to choose at 3, but remember we just said the function is not continuous there, so it's not differentiable there, so we don't have a slope at all. So not differentiable means f prime does not exist. So the only place we can have slope equal to 0 in this particular graph is at x equal to 0. We would have a horizontal tangent line. Because if slope equals 0, that means you have horizontal. Not a horizontal asymptote, horizontal tangent. Okay, that's the end of this particular set of notes.